Hi guys, I'm Ruby Chow, and this is going to be a little review for our final exam coming up next week on circular motion, which is a topic that we discussed around the middle of the year. So I'm going to go through some of the basics and then jump into a sample problem to help you learn more about circular motion and just how you're going to approach it on your test. So to start with, here we have a circle to represent a circular path that something would follow, and I've written a few arrows to show the velocity at certain points within the circle. So the velocity is tangential to the circle at these points. And as you can see, it looks like all the velocity arrows are exactly the same length, which means that they're the same magnitude. So you might be thinking, well, that means there's no acceleration, because when we talk about motion in one dimension or even two dimensions, we usually just say then it's constant velocity if the magnitude is the same. But we need to remember the definition of acceleration, which is just an overall change in velocity. So if something has a change in velocity, that can be either its magnitude or its direction, or both. And in this case, it is the direction. So because of that, we know we have radial acceleration in circular motion. And that just means that the acceleration is pointing towards the center of the circle. So if we bring back our little picture, we can see that if you draw the acceleration, it all points towards this center of the circle. And it's also important to remember the formula. So we have radial acceleration, a sub r, is equal to v squared over r, with v being velocity and r being the radius of the circle. You should remember that you should never use x and y axes exclusively for circular motion problems, because it'll just confuse you because you're moving in a circle, you're not moving along an x and y plane. So you should have a radial r-axis that points toward the center of the circle. So that's something that you would draw. So it's like how with incline problems we often would draw an axis that lined up with the plane rather than the ground, as it made things easier. So just in the same way, we want to include a radial r-axis that points for the center of the circle. We also want to make anything that's going in the same direction as this radial r-axis towards the center of the circle a positive value, because that will determine the positive, and anything going in the opposite direction will be the negative. And you'll see more of this as we go into our sample problem later on. Sometimes you need to draw a y-axis, but that's only if there are forces that are exerted on the object in a perpendicular direction to this object's circular motion. So that's like if somebody is skating in a circle and then the earth is pushing down on them and then the ground is pushing up on them. So those are y-axis forces, but you don't always have those, so that depends. Now here's our sample problem. So Josh drives his car at a constant 12 meters per second speed over a bridge whose shape is bowed in the vertical arc of a circle. Find the direction and magnitude of the force exerted by the car seat on Josh as he passes the top of the 30-meter radius arc. His mass is 60 kilograms. And this is from the PTPA textbook, chapter 4, example 4.4. So over here we see that we have this nice arc that represents the top of the circle. So we know that Josh is moving in a circular motion problem. This is the car, and the mass here is indicating the mass of Josh plus the car, but we don't really need that because we're looking at Josh as a system. So Josh is 60 kilograms, and that's going to be our mass that we use later in the problem. And he's going this way at 12 meters per second over there. So just keep all of these factors in mind. These are our givens. And again, we are looking for the force that the seat exerts on Josh. So this is just a blown up picture. As I said before, we need a radial r-axis that points to the center of the circle. So since this is the top of the circle, where do you think it would go? Well, I'll show you with this green arrow. So that's going to be our acceleration towards the center of the circle, because that's how it works in circular motion problems. So as a result of that, we're going to draw our little axis in the same way. So here is just a regular force diagram. It looks pretty simple when you think about it, because this part is the part that's going to be the radial axis. So the radial axis in the positive direction is from here to here, and it's going in this direction, and that lines up with the picture that we had in our previous diagram. And this is Josh, this little dot over there. So next we want to draw the force that the earth exerts on Josh. So that's pulling him down towards the center of the circle, or towards the earth. So that's going to be our pink arrow, the force that the earth exerts on Josh. In the opposite direction, we're going to have the force that the sea exerts on Josh. And now notice that, again, because the radial r-axis is going in the positive direction, according to how we label it, the force that the earth exerts on Josh is positive, whereas the force that the seat exerts on Josh is negative. And it's smaller because, as you can imagine, when you go over a hill, you're really being pulled down by the ground, so there's a net force going downward, or in the positive direction according to the radial r-axis. Now this is our formula for Newton's second law, modified slightly for circular motion. So the mass times the radial acceleration is equal to the sum of the forces in the radial direction. So we're going to substitute in v squared over r, which we learned earlier, in for radial acceleration. And then we're going to do the sum of the forces in the radial direction, so we know that's force that Earth exerts on Josh, which is again positive, minus the force that the seat exerts on Josh, because that force is negative. And then if we keep moving around the equation, then we get this, so that we're solving for the force that the seat exerts on Josh. Then we substitute in mg for force that Earth exerts on Josh. And we get this lovely equation that we can plug in all our givens into. And we end up with this final answer, that the force that the seat exerts on Josh is 300 newtons. So going back to our problem, we're going to see that this was what we were looking at, and we had all our givens that we plugged in earlier, and if we answered the question, which was find the direction and magnitude of the force exerted by the car seat on Josh as he passes the top of the 30-meter radius arc, then we get our answer of the car seat exerts a 300 Newton force on Josh in the upward direction.